Hi, in this lecture I'm going to explain some things that hopefully will make it easier for you to understand what's going on when we begin to write programs to solve problems. Uh, Thus far we've looked at HTML5 and CSS, a markup language and a formatting language, and we're about to start looking at an imperative language called JavaScript. And the things that we do with JavaScript are far more complex, and unless you have some understanding of the way a computer works in general, it's going to be difficult to understand why we're writing instructions the way we do. So I want to start out and just give you some general background information, and although from a practical standpoint you won't really be using this all that often or having to think about it real directly, it nevertheless will provide the right framework for which you then will begin to solve programming problems. So I want to start out by looking at several diagrams, and in diagram 1 I show the computer system in a way that allows us to see that at the core of everything is what we call the computer hardware, or the tangible components of the computer, anything you can see or touch. So, from the external part of my computer as I'm sitting here doing this lecture, I see there's a monitor, an output device, a keyboard, an input device. I have a touchpad that's also an input device. And there's a metal case that surrounds some other electronics that I have never really opened up and looked at, but nevertheless I know what they do and what some of the component parts are. So we have the computer hardware, which I'm going to discuss in detail, and you're familiar with that again because you see it and touch it all the time. And then in order to make that hardware function, it needs to interpret instructions. It needs to carry out instructions that have been provided to it. And that's the core of computing, is that we have this hardware, this machine that has the ability to do almost anything. Okay, sometimes it's called a universal machine, unlike a microwave oven, which can basically generate microwaves that can be used for cooking purposes, or a dishwasher that can pump water and provide some kind of fluid motion that cleans dishes. A computer's different, and it's different than almost any other device you can think of, probably any other device you can think of, in that it can do any number of things. It can be a word processor on one occasion. It can be a financial analysis tool on another occasion. It can be a window into the internet. It can be something that allows you to communicate with friends by way of Facebook. And, there are seemingly endless applications or things that a computer can do, and the reason for that is because that same hardware has the ability to interpret a current set of program instructions and react to it. And if the instructions say act like a typewriter, then it will allow us to create documents and store text. If the instructions say act like a flight simulator, then it allows us to engage in activities that would be something similar to what would be needed to do in order to fly an airplane. So this hardware has the ability to do any number, an endless number of things, so long as it is instructed in how to do it. So that's the hardware. The instructions that the hardware receives, that the hardware follows, are of two major varieties, two major categories. One collection of software or instructions is known as the system layer or the system software instructions. And these include the program instructions that are contained in the operating system. So if you have Windows 8 installed on your computer, then that would be instructions that in a logical way interface directly with the hardware, that controls the hardware, that optimizes the performance of the hardware, that protects the hardware from other malicious instructions. So as we think about the operating system, antivirus software, software again that's used to either control or optimize the performance of the hardware or protect the hardware from malicious instructions. Those are all examples of the kind of software that we're talking about here in this first black layer called system software. And it's absolutely essential that a computer have those instructions in order to be able to function, but at the same time, if that were the only instructions available to the hardware, very few people would have an interest in a computer. I mean, a computer really wouldn't be able to provide many practical benefits to people. So there's another layer of software, and the one that you're most familiar with, and the one that is the reason why people buy computers, and that would be the application layer. And in this class, we will be creating instructions that are in this realm of application software. We'll come up with ideas for things that will be useful for human beings, and we'll write instructions in a very specific way in order to have the computer perform that useful task so that it's of benefit to a human. Okay, so our focus as we develop content in this class will be not to create hardware, not to manipulate the hardware directly, not to write instructions that's designed to control and optimize the hardware, but rather to write instructions that perform tasks that are useful for people who will be developing applications. So what do those instructions look like? Well, you've already seen an example of, several examples of HTML5 and CSS, and when you first saw that language, you probably said to yourself, this looks, complicated, it looks cryptic. But at some level, as you've learned to work with it, you probably also realize that it is English-like. We use the characters in the English alphabet to construct identifiers like class selectors, and if you think about CSS, there are these properties that have some key word, and those properties are English-like in their name. So if you see a property like back color, that suggests something like background color, and you may not know every single detail of it, but nevertheless, as you look at that program code, once you've worked with it for a while and you've gotten some basic level of familiarity with CSS, it begins to make some sense and it's readable, and as you write your own CSS rules, then you've been encouraged to create CSS rules that are descriptive, that suggest the task that they're performing. And likewise with HTML5, we have an IMG tag, for instance, an image tag, and we have a tag that has an href attribute, a hyperlink reference attribute. And so, I'm not saying that it reads like a well-written novel, but on the other hand, a human being can read HTML, can read CSS, can learn HTML, can learn CSS, and as we'll find out, the same thing is true of the next language we're about to learn, called JavaScript. They are at some level English-like. but they're made English-like so that human beings can develop software so that human beings can relate to the language as they explain the solution to their problems. But at some level, the hardware level, the computer cannot understand H1, it can't understand IMG, it only understands a sequence of high and low voltage states. Or, if you think of it in more human-like terms, and I know that you've seen this, represented in books and movies and in a number of different, forms of print, where we show the internal representation of the instructions that the computer reads as a sequence of ones and zeros. Okay, so those ones and zeros really map, in a one-to-one correspondence to a high voltage state or a low voltage state. And so where we have a 0, it represents the occurrence of a low voltage state, and where we have an occurrence of a 1 represents a high voltage state. And at some level, the hardware only understands those individual voltage states, and from those individual voltage states, it is able to figure out what the human being wants it to do. Now, this gets kind of complicated, so that's why I wanted to give you this background. So coming out of this first diagram, understand that a computer system really consists of the hardware, the system software, and the application software. And they have to work in concert in order for the computer system to produce any kind of meaningful activity that is useful to the human being. Understand that as human beings who are in the process of developing software, we're going to write our instructions in a English-like form, but somehow, as will be explained here momentarily, those instructions are ultimately given to the hardware in a binary format. Think of it as ones and zeros, but really that binary format from the computer standpoint is going to be a sequence of high and low voltage states. All right, so hopefully that begins to click a little bit. Now, what is the hardware? Well, I mentioned the hardware is, what I see on the outside, the keyboard, the monitor, the mouse pad. It's also a lot of other things, and I want to discuss the computer hardware, that center circle. I want to discuss the computer hardware. I want to focus on the computer hardware now using a diagram that was developed in 1945 by an American mathematician named John von Neumann. So John von Neumann was the premier mathematician in his day. He was involved, among other things, in the Manhattan Project. So he worked on the development of the atomic bomb during World War II. And also in World War II, the other great invention that occurred was the first computer. And although von Neumann did not really work much on the first computer called the ENIAC, he was actually put on the project at the very end of the project, but for most of the project's life cycle he was not involved. But at the very end he was involved, and he was given the responsibility, commissioned with the task of developing a proposal for any future computers to be developed. The first computer that was developed during World War II for the purpose of doing calculations to produce ballistics tables for the artillery was a computer called the ENIAC. ENIAC, Electronic Numeric Integrator and Calculator. So the ENIAC was developed, as part of the war effort to perform some rather complicated computations in order to generate the tables that are necessary to fire artillery equipment in the heat of battle, given certain atmospheric conditions, temperature and wind direction and so forth. So it was very difficult to do all these calculations manually, so the Department of Defense funded a project to build an electronic calculator, brand new idea at the time, called the ENIAC. And although the ENIAC was completed and did what it was intended to do, it became apparent as a result of building the ENIAC that there might be a need for future computers. So this government-funded operation then concluded with John VonNuemann doing an analysis of the ENIAC project and making a proposal for the next big computer project called the EDVAC. And in this proposal, VonNuemann suggested some things that are still used with computers that are built today. And this basic design architecture is known as the VonNuemann architecture. This MacBook that I'm working from right now, that I have partitioned into both a Windows and a Mac partition, rather sophisticated computer, is actually a computer that is based on the VonNuemann architecture. All computers still are. Okay, so this was a great idea that he came up with, and what he suggested, and some of it seems very obvious, but he was the one that was commissioned with the project and was the one that provided the first specifications on how to build the wheel. What VonNuemann suggested, and this should be pretty obvious, is that in order to have a fully functional computer, there needs to be a component that provides the system with input. Now he didn't suggest that there be a mouse and that there be a touchpad and that there be any specific device, keyboard. He just said that in this rather straightforward, what's known as a block diagram, he said there needs to be some component that provides input, so that human beings can provide data and instructions, so that they can provide the instructions for the computer to follow in order to perform the task, so that they can provide the raw facts and figures, the numbers, the characters, and so forth that are necessary to do the processing. VonNuemann had no idea in his day that eventually in the year 2014 there would be some computer science instructor that would be using a computer built on this architecture that would be using a microphone as an input device. Okay, so he didn't bother himself with the details of specific devices, but he said that there should be some kind of input unit. He also said that there should be devices, or there should be some kind of output unit. So it does little good to have this chunk of hardware and to be able to provide it instructions and to have it do the processing necessary to transform the raw data into some finished product, unless you can see the result. Okay, unless you can experience the result in some way. So he didn't say computers need a monitor. He didn't say that computers need speakers or anything like that. He just said there needs to be some way to take the results of the computation and present them back to the user. He also recognized that there was two forms of memory that a computer would need. It would need two forms of memory to store both instructions and data. Okay, again, so data, if my explanation isn't sufficient, look up the definition for data, but it's basically the raw facts and figures that a computer uses in order to process further this raw material into a finished product. And what VonNuemann recognized was that the computer needed to store two basic things: data and instructions. And it needed to store the data and instructions long term, and then when the data and instructions were immediately needed for processing, they needed to be copied into another form of memory, which he called primary memory, so that that active program and the data that that active program uses could be made available to the brains of the computer, which he called the central processing unit. So nowadays we use maybe hard drives or USB drives. I'm using this Macintosh that has a solid state drive, but our long-term storage, where we keep the operating instructions, the operating system instructions stored, where we keep our applications like Microsoft Office and Expression Web and any number of other programs, where we keep these stored long-term, is on disk storage or solid state storage nowadays. In years past, that may have included things like magnetic tape and key punch cards. So a number of different devices have been used in the past to serve as secondary memory. But whether it's key punch cards or whether it's solid state circuitry, there is a need to store the programs and instructions long term, so that anytime they're needed, they can be called up out of this long-term memory and then put into primary memory, where they will be available immediately for processing. And so our primary memory is nowadays something called RAM, random access memory. To a limited extent, we use other forms of primary memory like ROM, read-only memory, or PROM, programmable read-only memory. But in most computers, if we're thinking of what's going on under the hood, we're really looking at the disk drive being disk drive, or disk drives being secondary memory, and we're looking at RAM as being primary memory. And so, if you go buy a computer, even if you don't know much about computers at all, you should at least have this fundamental understanding of things, or otherwise you're going to go to Best Buy or wherever it is you go, the Apple Store, or wherever it might be, and you're going to end up buying a computer that either is inadequate for what you're doing, or perhaps maybe paying way too much money for a computer that has far more processing power than you need. So if you have some understanding of how this works, it's going to allow you, if nothing else, to make more intelligent purchasing decisions. You can't escape a computer purchase without having some understanding of secondary memory, primary memory, and input and output devices. Now, the other thing that VonNuemann suggested was that there needed to be something that he called the central processing unit. This is really the brains of the computer. This is where the processing goes on. And what he thought was needed was something called a control unit. And a control unit are electrical circuits that are designed to read and decode and carry out program instructions. Okay, so I'll have more to say about that here momentarily, but this is really where the rubber meets the road. This is where the hardware and the software are able to converge. The critical, if you had to ask me what's the most critical component of all the computer hardware, I would say the control unit within the CPU. The control unit is the circuits that are designed to sense the high and low voltage states that make up the software, and it is designed to interpret them and carry out those instructions. So that's the control unit. Really a fascinating thing to think that there is an electronic device that has the ability to take electronic signals that are derived from a human being's thought processes and decode those high and low voltage states and tell the computer to carry out a specified task, that's, you know, where everything converges. The hardware and software converge. Von Neumann recognized that the computer would need to do a number of computations, so he suggested that there be circuits that were designed specifically for performing the basic arithmetic operations. And these arithmetic operations can be used, you know, for a variety of purposes, ranging from crunching numbers in a spreadsheet to generating graphics, to, you know, deciding how to transform the picture elements on the screen in order to create some kind of illusion. So anything that has to do with graphics ultimately involves a lot of mathematical processes that are carried out by the arithmetic logic unit, sometimes called the ALU. He also recognized that there needed to be high-speed hardware devices that could manipulate the individual bits or the individual binary digits. And these are called these storage devices, these really fundamental storage devices that are used for holding the data as it's being processed and holding the current instruction as it is being executed. These very high-speed storage devices that are inside the CPU are known as registers. And I've made note that there are registers that are special purpose, like the program counter and the instruction register, and then there's also general purpose registers. Now, I'm not going to go mile deep into any of this because this is a full-blown course if you do a computer science major. And if you don't do a computer science major, you're not going to have need for that detailed information. But everything I'm explaining here can be explained in far greater detail. There is so much more to understand that you're really only getting a very superficial, surface level presentation of this. But nevertheless, what you should understand is that a major part of the computer is the central processing unit, CPU, and that it contains the hardware component that allows the hardware to interpret the software and carry it out. It also contains specialized circuits to perform arithmetic operations for a variety of purposes. It also contains storage devices called registers that store both data and program instructions as they're actively being processed. This entire central processing unit is what you would see if you went into Best Buy and purchased a computer and looked down and saw a label that said Intel or Intel inside. You might see that it is an i5 or an i7 computer that you're purchasing. All this has to do with central processing units. So there is a company that manufactures central processing units that are used by Apple and Dell and whatever the other HP, whatever the other computer companies are. And the central processing unit that is most frequently used is made by a company called Intel. Okay, they are not the only manufacturers of CPUs, but they are the principal player, the principal manufacturer. Okay, so that's the von Neumann architecture in a nutshell, and let's continue on. Now, we're going to be writing program instructions, and we're going to be learning a language called JavaScript. Okay, I want to change this, actually a diagram that I used in another class. So the language that we're going to use is called JavaScript. It's an English-like language. You'll see English keywords like for and while and if and else and things like that. And it's readable in much the same way that HTML5 and CSS are readable. And, you know, again, if you're learning to program as you learn JavaScript, you're going to go, this is the hardest thing I've ever seen. Now, you won't say that, but you'll be challenged by it. But you got to understand that language is what's called a high-level language, or sometimes another word that's used more or less synonymously is source code. And that source code language is going to be, by and large, English-like. Now, in the CPSC 1400 class, which is the class that I originally prepared this diagram for, we program in a English-like high-level language called C#. In this class, we will be programming in a language called JavaScript. Now, both C# and JavaScript are derivatives of an older language called C. Now, if you learn how to program in JavaScript, it makes learning how to program in C# much, much easier. So I know there's some people in this class that are going to go on and do a computer science major, that are going to go on and take CPSC 1400. When you do, you're going to be very glad, that you took this class. You're going to really have a nice background for what we do in 1400. But in any case, that's the language we're going to use. Again, that's known as a high-level language, or sometimes we refer to it as source code. Our specific language is JavaScript. Now, ultimately, that language, these instructions that we create in order to solve this task, the instructions that we develop for our application, ultimately have to be rendered into a binary format, into the equivalent of a string of ones and zeros. So how's that going to happen? Well, back in the old days, in the days of the ENIAC, the very first computer that was created, the computers did not have something called a language translator. And for a human being to write a program that would be interpreted properly by the CPU, the human being had to write the equivalent of ones and zeros, had to develop their program in a binary format. And it was even worse than what I'm describing. It was tough. It was hard. You almost had to be an electrical engineer in order to be able to program a computer, because you had to understand things down to the circuit level. You had to know exactly which switch need to be opened or closed at any point in time in order to make some task occur. And so it was a nightmare, and fortunately in the 1950s, the real contribution to computer science was the development of what are called language translators. And there are two basic ways these high-level English-like languages can be transformed into a binary format that the CPU can actually understand. One way to do it is to compile it, the other way is to interpret it. So there are manufacturers of programs that are designed to translate certain high-level languages into the corresponding binary format. And in the context of programming web pages, that language translation is done in the client's browser. So the client's browser contains the language translator, and the variety that it contains is called an interpreter. Now, real quickly, the difference between a compiler and an interpreter is that if I use a compiler to translate my source code, it will save the executable file. It'll save the ones and zeros, and then if I want to run that program, over and over again, for instance, like the operating system of a computer, if I want to run that program over and over again, then I don't have to translate it from high-level language to binary before I run it. I simply translate it one time, store the binary format, and thereafter run or execute that stored binary format. In the case of an interpreter, it always translates and executes, translates and executes. It'll translate a statement, execute it. Go to the next high-level language statement, translate it, and execute it. But it saves none of it in the process. Okay? It makes for a simpler way to do the language translation, but it's less efficient than a compiler. But for processing web pages, that is done by language translation, because we really don't want to save the binary format of every single web page that we encounter. Okay, so we're going to be using a browser's interpreter in order to get our statements that we write in JavaScript ultimately in a form that the CPU can understand. And that is done more or less automatically. So what do you have to do to tell the interpreter to begin processing? Not really much, okay? Not much at all in working with web pages. So as we get into that in a practical way, I'll point out what's going on. I'll relate back to this diagram. But what I want you to do is, as you think through the problems that you're solving, and as you write the programs to solve those problems, have in the back of your mind the correct understanding of what is going on under the hood. Ultimately, whether compiled or interpreted, the high-level language is translated into the appropriate sequence of ones and zeros, and it's those ones and zeros that are then processed by the CPU in order for the task to be carried out. Okay, so that's a quick overview of language translation, something you should have in the back of your mind. The next part of the diagram deals with something called the input-output cycle. And this is a real simple diagram, and it's what I might describe as computing in a nutshell. So when we develop an application, what we're really looking to do is to provide a set of instructions that have the ability to take some kind of raw data input, transform it in some way into some desired output. Any program that you can think of that works on a computer basically does that. It takes some raw data, transforms it somehow according to the program instructions that we write into the corresponding information that's useful to the human being. Excuse me. 5, the machine cycle. Now, what I'm presenting is a very simplified version of the machine cycle, and what I'm looking at is how does the computer actually process the executable code. Okay, so we're focused on these two parts, on the CPU and the executable code. Once that code has been translated into a binary format, how does the CPU actually, deal with it? And what von Neumann proposed is this, and again, this is a kind of a simplified version. There's more to this, but I've tried to distill it down to the basic steps. And again, if you go on to major in computer science, you'll learn this in far greater detail in a computer architecture class like CPSC 2400. But in general, here's what happens. There is a register, a high-speed storage device inside of the CPU called the program counter. And the program counter is designed to store the current, the address of the current instruction in memory. The address of the current instruction in memory. And when I say memory, I'm talking about the computer's RAM. So remember, going back here, that inside the CPU we have registers, one of which is the program counter. And we have programs, which are instructions, and we have data, which are the raw facts and figures. They're stored long-term in memory, but when we need to execute a program, those instructions and that data is copied into the computer's RAM and stored at addressable memory locations. And so when a program begins executing, the first thing that happens is there's this special register called a program counter, and it will store the address in RAM at the first instruction of the program. And, getting back here to my steps, program counter set to the first instruction. I made a mistake. I'm going to change this real quick. Now, correct it. I'll talk about that here in a moment. So the program gets set to the first instruction. That happens one time only. Then the instruction at that address is fetched by the program counter. fetch the instruction at the address in the program counter. That instruction is fetched and the instruction is found by the CPU looking at the value of the program counter, then going to random access memory and getting the instruction at that location. That instruction will consist of a series of ones and zeros. That instruction that is fetched will be put into another register called the instruction register. And at that point, the length of the instruction is added to the program counter, which has the effect of bumping the program counter's value up to the address of the next instruction to be executed. So now the program counter is pointing at the next instruction to be executed. And basically that's what the program counter always does. It contains a value that corresponds with a memory address that is equal to the memory address where the next instruction to be executed can be found. So the program counter gets bumped up. The program counter then, the control unit then decodes the instruction in the instruction register, and that instruction has two parts, something called the opcode, which specifies the task to be performed. Maybe it's an add, maybe it's a divide, some kind of instruction like that. And it also contains another part. The second part of the instruction is a numeric value in binary format, a numeric value that corresponds with the memory address in RAM where the data that's needed by that instruction can be found. And so I've short-circuited this explanation, but basically there's another fetch that has to occur, or a sequence of fetches that have to occur in order to get the data that's being processed stored back into the general purpose registers in the CPU. And then once the general purpose registers contain the values of the data that's found at the address of the operand, then the control unit can tell the rest of the computer how to perform the task. And when that task is performed, the current instruction will be executed, and so control passes back to step B, not step A as I had originally put it, but back to step B, where the instruction at the address of the program counter is fetched and put into the address register, and then this whole thing goes through over and over again until the last instruction of the program is executed. This is, again, an oversimplified version, but I just want you to, understand that the programs that we develop in JavaScript have to be translated into a binary format. Then those instructions, when they're executed, are going to be fetched into the CPU. They're going to be decoded. That will involve getting more data in the process to actually use with that instruction. And once the instruction and the data that it needs is stored in the registers within the CPU can direct the task to be performed by the other hardware components. At that point, the current instruction is done, and the cycle repeats by consulting the program counter, fetching the instruction at that address, bumping up the program counter, and so forth. So look over the details, and I tell you all these things to give you some kind of background so that as we write our programs and we talk about things like variables and we do some other things, that what we're doing in JavaScript, hopefully what we're doing in JavaScript will make more sense. And hopefully this is good background information so that as you write your programs, again, it's not just a lot of smoke and mirrors. You really have some gut feeling for what's going on under the hood. That concludes this lecture.